In unpaired domain translation, we're concerned with the question, how can we learn to translate a source distribution into a target distribution? And here, two important evaluations are considered. First, the fitting, how well is the target distribution approximated? And secondly, the mapping, which parts of the source distribution are translated to which parts of the target distribution. And in this work, we were mainly concerned with the second point. How can we obtain a meaningful mapping? And one way of doing this is optimal transport, with the idea of transporting a source into a target with minimal cost. And in the discrete setting, this boils down to the following optimization problem, where you first compute a cost matrix between all source and target points, and then you optimize for the optimal coupling matrix P. Here, P represents how much mass each source point should transport to each target point, which you can see roughly sketched on the right. Now, this optimization problem has two constraints. The first being you want to translate the whole mass of your source, and you want to cover the whole mass of your target. Now, if an optimal transport map between a source and a target distribution exists, this is known as a Morse map. And recently, neural Morse maps have gained a lot of attention. Here, the idea is to learn a parameterized map that approximates this optimal transport map between two distributions. And this then provides you with a functional mapping that you then, for example, can apply to unseen data points, which you can then translate, giving you a notion of continuous optimal transport. And over the last years, multiple learning schemes for neural Morse maps have been proposed. And one of them, for example, is OT flow matching, where the idea is to build an OT map as the flow induced by a neural velocity field. And how do these neural Morse maps then look? So, for example, here roughly sketched is the EMness data set, where you have digits in your source, 8s, 0s, and 1s, and letters in your target, B's, O's, and I's. And you can see that now we learn to translate these with minimal cost. However, there's a distribution shift between source and target with respect to the classes. This is why now 8s are also translated to O's in this setting. And this is where unbalanced optimal transport comes in. In the discrete sense, here again, we optimize for the coupling matrix P. And the idea now is to replace the mass constraints with a penalty term that penalizes mass deviations. And this is based on phi divergences such as the KL divergence. Now, if we don't enforce these mass constraints anymore, we change the amount of mass that is transported in the source and target distribution. However, it is not clear how to incorporate unbalances into neural Morse maps. And the main contribution of our work is we show how to incorporate unbalances into any Morse map estimator. And this is done based on a two-step procedure where you first reweigh your distributions based on these unbalanced mass variations, and then you solve a balanced optimal transport problem between those two. And how does this look in practice? So if you would just learn a neural Morse maps, you would get this account for this distribution shift, which you might not want. But with our method, you first reweigh your two distributions. So you now see that the relative mass of the source and target distribution has changed. And if we now learn a neural Morse maps, we get a more desirable mapping than without unbalancedness. We showed that unbalancedness improves performance across a wide variety of unpaired translation tasks. On EMness, as sketched earlier, it improves visually and numerically. And same for high-dimensional image translation, like on Celeb A, where you can see that unbalancedness helps to preserve relevant input features. Additionally, we benchmark across two unpaired single-cell translation tasks, mainly single-cell trajectory inference and modeling of drug perturbation, where we show again that unbalancedness improves performance. Summarizing, we show how to integrate unbalancedness into